Hi, I'm Alistair, I'm a games designer, and in this video I'd like to teach you how you can make an electronic mastermind game like this one, using an Arduino, an LED matrix, some buttons and a maglock. Now, if you're not familiar with Mastermind, this is a game in which players must deduce a secret code by making a series of guesses. So suppose I wanted to guess that the code was 0000. When I press this button here, I get some feedback on this circular LED in the middle. In fact, I get a quarter of the circle light up green. That lets me know that one of these 4 digits is in the correct place in the secret code. So now I'll guess again something different. So let me guess 0, 1, 2, 3, for example, and press the guess button again. When I do this, I now have 2 quarters of the circle light up, and a third quarter is flashing yellow. So this lets me know that 2 of these digits are now in the correct position, and a third one does appear in the secret code, but it's in the wrong place. So based on a series of incremental guesses and adjusting future guesses based on feedback, I could actually work out that the secret code in this case is 0324. And when I now press the solve button, what will happen is the maglock releases and shoots the capture across the room. Now, if you were using this in an escape room or something like that, you could use this to open a door or a chest or a lock of some sort, or you could simply have the 4-digit code at the top here being the solution to a regular padlock. Now, I'm going to explain all of the electronics and the code and how to create this in a moment, but before I do that, I wanted to go into a bit more detail about some of the design decisions I made about the changes I made from the original Mastermind game into this version here. In the original Mastermind game, the secret code is composed of a sequence of 4 coloured pegs, chosen from a set of 6 different colours. Now, that's not great from an accessibility point of view, because if you're colourblind, you're put at quite a disadvantage as a player. I also had a kind of a technical constraint that I wanted to use these LED matrix displays, but they can only display red. So I chose to use numbers instead of colours as well. And also that seemed to fit in with the escape room context well, because it meant that the solution that players obtained would be a 4-digit number, and that could be the combination that they enter into a padlock, for example. The problem with this approach is that it's massively increased the possibility space. If you're choosing 4 colours from a set of 6, you have about 1200 different possible solutions. If you're setting a 4-digit number, that's obviously 10,000 different combinations. And that brings me on to my second change, which is that in the original game, players are only given 10 guesses in which to find the secret code. In fact, it's always possible to win in under 5 guesses, but if I'm allowing numbers, or perhaps you even want to allow letters or symbols, let's say, I need to increase the number of goes that they're allowed. And in an escape room context, I'm not even sure it made sense to limit the number of goes, because I don't know what I'd do when players hit that maximum. I'm not going to just lock the puzzle out. So I decided to remove the guess limit completely, and players can press the solve button anytime they want, and they will get feedback on their most recent guess. This is related to my third change though, which is that normally in Mastermind you get to see the history of all your previous guesses and the response that you got as a result. But if I'm allowing an infinite number of guesses, there's no way I can display an infinite history. So I decided to make it so that you only ever got feedback on the most recent guess. But this actually introduces a slightly new mechanic as well, because rather than it just being a case of pure logical deduction now, to work out the correct code actually requires an element of memory as well, because you can see the feedback on the current guess, but when you sort of change it and you try something else and you get a different result, you need to remember what the code was and what previous feedback you got was. So, it's a few adaptations from a classic game, which I hope go some way to explaining how I've made it, I feel, more suitable for use in an escape room context. So here's how I've got all the components wired together. I've got my Arduino Nano down here, and I've got my 4 button inputs that players press to change the symbols on these 4 LED matrix displays at the top. This is the button they press when they actually want to submit a guess, and then I've got the Neopixel ring here that gives them feedback on that guess as to how many of the symbols were correct. And then I've got a relay at the bottom that controls power to this maglock, which is going to release when they actually get the code correct. So just sort of looking at those individually in a bit more detail. So if we start off with the button inputs here, so you can see on one side of all of the buttons I've got connected to ground on the Arduino, that's via this black wire here. And then they all on the other side have a unique signal pin, which is going to, on this side, pins D2 to D5. They're the buttons which are going to change the symbols. And then D6, this one at the bottom here, that's going over here to the submit pin. So I've got four input buttons there, followed by one guess going to 2 to 5 and then 6, and they all have ground. And then the LED matrices themselves. So the LEDs I'm using kind of have an SPI interface to them. And normally when you have an SPI interface, you use particular pins on the Arduino. You use 13 for the clock and 12 and 10 for the Mozzie and Miso, for example. But the particular library I'm using for these actually allows you to use any pins on the Arduino, and it kind of emulates the serial SPI interface through bit banging. So I'm actually using pins A0, A1 here and D13, but you can actually use any pins you want to go into here. So I've got the data input or Mozzie, I've got the select, and I've got the clock line here, and then I've also got 5 volt and ground going to those pins as well. So this red line here, this is taking 5 volt to any components that need 5 volts. So it's going down to the relay, it's going across to the Neopixel, and it's also coming up to the displays up here as well. This black line is always going to be ground, and then like I say, you've got 3 data pins, and they daisy chain between all 4 of these displays. Now you can actually connect these individually if you want, and you can add more onto the end as well. I bought a unit that kind of has 4 displays already connected together. So this wiring was kind of already done for me, but I'm just displaying how it is there. So the first input here has the data input to it, and then the data out of this one goes into the data in of the next, and they kind of chain together. So that's how they work. And then I've got the Neopixel ring here. So this also has got 5 volt and ground going into it. Although notice I've also got a capacitor across those lines. So this is kind of recommended whenever you use a strip of these WS2812 LEDs or Neopixels as they're sometimes known. So I've just got a capacitor here. This is a 1000 microfarad or 1 millifarad capacitor, 6.3 volts, just between. So I've got the negative leg here, the one with the stripe, that's going to ground, and I've got the other leg going to the 5 volt supply here, and sort of quite close to the ring itself. I've also got a resistor here. This is a 330 ohm resistor, which I've got on the signal line. So this is going into A2. Again, you can use any pin you want for this, so long as you set the same matching code in your Arduino code. I'm using pin A2 just because it was convenient and on the right side of the board. So that goes into the data in line on the LED, so over there. And then down the bottom here, so I've got a relay, which once again has got 5 volt and ground going into it, and it's also got a single signal line that is going into A3 in my case. And what happens is that when this pin here, when the Arduino writes a low or a high signal to that, it's going to energize or deactivate the relay coil here, and that's going to cause on this side the common terminal to flip between normally closed and normally open. Now with the type of maglock I'm using, so this is a cabinet style maglock, and it's what's called a fail secure maglock. So when no power is supplied to this actually is locked. That's its default state. So I want the default to go into the normally open connection on here because I don't normally want it to have any power going to it. So I'm using the normally open, and then I've got the common terminal of the relay load side here going to a 12-volt power supply. So when when nothing happens in the regular state of the puzzle, these two are not connected because this is a normally open connection. When the puzzle is solved, the Arduino will write a signal to this line here. That's going to cause the inside the relay, it's going to flip across and connect these two. That's going to close the circuit here. 12 volt will go to the maglock, and that's going to eject the catch that's here. Now with these type of maglocks, it's very important that once the catch has been ejected though, you need to cut the power again. So they don't have any kind of permanent ongoing power requirements. You send just a pulse of power, so I'm just sending it for a very brief amount of time, well under a second. That's enough to eject the catch. And then I'm going to toggle the signal line again to flick it back to normally closed so that the power is cut again. So that is everything, how it's all wired together. And here's the sketch that's running on the Arduino. Now there's quite a lot here. It is relatively complex. I've tried to comment it as well I could, but I'll also kind of step through it line by line just to explain what's going on here. So as always, I start my code with a section of include. So this is additional code files outside of this sketch here. And I'm using a couple of external libraries here. The first one I'm using is something called Fast LED. This is a library that's really useful for controlling all sorts of LED strips. And in this case, I'm using that to control the ring of LEDs, which is going to provide feedback to a player's guess. You can download it from there. I'm also using something called LED control, which you can get from this GitHub link, and that is going to help me control the matrix displays at the top that actually display the symbols or the digits of the code that the player has chosen. Arduino JSON is a library for creating JavaScript object notation data structures. So this is a little bit complicated. What I'm going to do is a bit later on, I'm going to send some values over the serial connection whenever a player makes a guess. And I've done that in my previous projects, normally by using serial.print to send some text strings. Now in this case, I'm not going to send text strings, I'm going to create something called a JSON object, which is kind of like a structured packet of data. You can still read it, but it kind of looks slightly more complicated. But the reason I'm using that is because that makes it easier to receive that data in another program. So in my case, I'm going to use Node-RED, but you could also use lots of escape room monitoring software to receive updates from this controller as to the state of the puzzle. So I'll go into that a bit more detail later. And I'm also including, this is a local additional header file, and I've actually got that open here. So the only reason for putting this into a separate file is just to kind of reduce the clutter here. So it's this file here that actually defines what all the different symbols are that are going to appear on the matrix display. So you can see each one here is an array of 8 bytes. So if I told you that this was actually the digit 0, what I hope you can see is that the ones in this sequence here, they represent the LEDs that are going to be lit up to display that character. So we've got a solid line at the top and bottom, and then sides with the gap in between. Obviously the number 1, well, that's just a straight line of ones down the middle. But you can really use this kind of data structure here to represent any values at all. They don't have to be numbers on the display. So like I say, I put some examples of some letters in there as well, as also a little space invader here. And in fact, there's an entire alphabet down the bottom here. So this is, rather than having all this included in my main Arduino sketch file, I've just moved that into a separate header file and included it at the top. It's just going to make it a bit easier to read. Okay, then we get onto the constant section. So these are values which are going to be defined here at the top of the code and are not going to change throughout the duration of the code. So I've got those pins which I had the buttons attached to. So remember, one side ground and another side going to this input here, and that's where the submit pin is going. This is the output pin that's connected to the signal line of the relay. This is how many elements are actually in the code. So we've got 4 buttons here, and we've also got 4 matrix displays, so obviously that's going to be 4, but you could in theory make that any value you want. And then the number of symbols is the number of different symbols that can be in each of those code positions. So here we've got a code of length 4, and with each one of those having 15 possible values. Okay, and then finally, how many LEDs are going to be used to light up to show the player how many guesses they've got. So in a simple case, I could make this equal to the code length, and each LED corresponds to one possible match. But because I had that sort of circular ring Neopixel, I thought that actually looked nicer to have a whole segment lit up. So I'm actually lighting more than one LED to represent a particular response. So in this case, I've got 24 in that ring. You could possibly simplify that if you just wanted to have one LED per response. You could make that a bit simpler. Then we've got the globals. So these are values which are shared throughout all the different functions of the code. And we start by initializing an instance of the LED control. So this is what's going to control those matrix displays at the top. And as I sort of mentioned when I was doing the wiring, it uses 3 pins. So we've got the data pin, the clock pin, and the chip select pin. And also we specify how many modules we're going to have, how many different displays we're going to have. So I've hard-coded 4 there, but in fact that's always going to be equal to code length because we're going to have one display for each element in the code. This is to identify when players have pressed a button. We're just going to keep track of what the state of each button was. This is actually where we define what the solution is going to be. Now, I've hard-coded a value in here, 0324. So every time you run this puzzle at the moment, that is always going to be the answer. If you wanted to have a dynamic code, so that, this would be good to have a static code if you want it to be the solution to a padlock, for example. You're going to want it to be the same each time. But you could, if you wanted to, have a dynamic code, and that can be overwritten. I've included a function that does that just down here. This variable here, this keeps track of what the player's guess was. This is how many guesses the players have made so far. And we also just create a global object that's going to keep track of which LEDs are lit. Okay, so then we actually get through the functions that are going to do something. Like I said here, this function here is kind of optional, but if you wanted to reset the code to a random value each time, this is a function that will do that. It does it by reading an unconnected analog pin. So A5 I haven't assigned to anything up here. I'm not using A5, it's just an open pin, and as such it's going to kind of read a random amount of noise when it's unconnected. And I'm going to use that noise as a seed value into the random number generator, so that will give me a different value each time. And then I'm just going to fill up the secret with random values that lie within the range of the number of symbols we've got. So this will give a random value between 0 and num symbols, which was I think 15 in our case, wasn't it? But this is optional, you don't have to use that if you want. And then what we'll do, actually, let me jump to the end slightly and I'll step you through the setup and the loop function first. So first of all, in the setup function, so this is called when the sketch first starts, and this kind of just initializes everything. So we'll turn on each of the displays, so we'll loop over all 4 modules, and then this, we call it sounds a bit strange calling shutdown, but we call shutdown but with a false argument, so that's kind of like the opposite of shutting down. That wakes them up, that sets how bright they're going to be, and that just clears them. So we do that for all 4 displays. Then we initialize the 4 input pins, and we also initialize the submit pin. We're using input pull-ups because remember the other side of the button was connected to ground. So by default they're going to read a high signal because of the pull-up here, and then when they are pressed they're going to read a low signal because the button is going to be connecting that GPIO pin to ground. We initialize the relay as an output because that's what we're going to send the signal down, and we also have it as a low output to start with, just so we don't want to activate the relay to start with. We'll initialize the serial connection, and we'll also initialize our LEDs. So I'm using, this is the type of LED display I'm using, WS2812B. That is the data pin. Now, unusually, you'd normally refer to RGB color ordering, but not all LED strips use RGB coloring, and these strips particularly actually use GRB. So the order in which the bytes of data are sent representing the different colors come in green, red, blue order instead. If you ever have LEDs that kind of seem to be oddly misbehaving and are displaying the wrong colors, that's something that's worth checking, by the way. So we'll initialize our LED display and we'll tell it how many LEDs we've got. This is the line here that initializes the random code. So if you wanted to set a random one, you could simply uncomment that like that. But at the moment I've got it uncommented out. And then in the loop, what we do, we kind of process the same sequence each time we're waiting. So the first thing we'll do is we'll actually wait for the players to guess a code value. So that's what getInput does. We'll have a look at that in a second. And then what we'll do is we'll create a response to whatever their guess was. So I've got two counters. I've got the number of whites in the response to their guess and the number of blacks. And then I call this calculate response function to actually work out what those two values are. And then what happens here? Well, if the number of blacks returned by this calculate response function, if that's equal to the code length, well, that means that every element in the code was a black, and that means that the puzzle was solved. When I say black here, I mean, in my example here, I was displaying green quarters of a circle, but black's what it's in the original Mastermind game. So that's the correct symbol in the correct place. So that's the whole code is correct if this is true. So we'll write a high signal now to the relay pin, like I say, just for 50 milliseconds, so not very long at all, just a brief pulse. That's going to be enough to allow that 12-volt supply to unlock the maglock, eject the catch, and then we'll write low again, so we will cut off the power again after that, and we'll just write a silly little message just to say that something's happened, and we'll flash the LEDs in a chase sequence. So we'll loop over all the LEDs, set them to green, wait for a bit, and then we'll loop over all the LEDs again and set them to black. So this is just going to kind of make them all light up. If it was incorrect, then what we'll do is we'll provide the feedback to the player on what they said instead, so that's display response, and we'll increase the number of guesses. So that's the process, and that just loops forever. So now let's have a look more in detail at what those particular functions do. So getInput, that's the first one. And if we just scroll back up here to find getInput. So I've got a section at the top here that I've actually commented out. When I was writing the code and I wanted to test it, rather than pressing the buttons each time, I just wanted to input some values over the serial monitor. So that's what this section does here. It's not currently used in the puzzle I demonstrated, but I thought I'd leave it in because you might find it useful for when you want to do a similar thing. So what it does here is it uses serial available to see if any keys have been input over the serial connection. So I mean, when you go to serial monitor here, for example, you'd just type the value at the top of the line. And if that's true, it reads those bytes, it assigns them to the guess, and then it carries on. But the one we're actually using in practice in the game actually is the one that uses the buttons instead. So that's what this bit at that's not commented out does. So the first thing here, I wanted to make sure every time the players press the submit button, I want to make sure that they only get the guess submitted once. So the first thing that happens here is that if the submit button's actually being held down, we're going to wait, and we're just going to loop over there. So we want to make sure that we're not double counting or submitting guesses for every millisecond that the submit button is held down. That's what that does. And then what we'll do is, while it's not being held down, we'll loop over each of the buttons, we'll read what their current state is, and if they weren't being pressed in the last frame, but they are being pressed now, that means that we know that we've detected a new button click, basically. That's what that line means. So we'll increase whatever the guess that corresponds to this button is. So if we're on the 0th button, we'll increase the 0th guess. So that's the first element in the array. Then we'll go over it again, and if we're on the first button or the second or the third, we'll increasing the corresponding guess value assigned to that button. If we end up pressing the button so many times that we get to the end of, we've been through all the symbols that we've assigned, then what we'll do is we'll kind of loop back round to the beginning again. So we'll set the guess value to 0. That's what that line there means. And then we'll update our stored value so that we know whether the button was pressed this frame or not. That will help us next time we loop round. And then we'll actually need to show on the matrix display what the increased value is. So we'll call this lc.setRow function. So this is going to set a whole row of LEDs on the matrix that corresponds to the button. So we've got 4 buttons, remember. We've got 4 elements in the guess, and we've also got 4 matrices or matrices. And that I value is keeping them all in sync, basically. So we'll set the ith matrix, and we'll set each row in that matrix to be the row of bytes from this digits array. So the digits array, this is what we had defined in our font value. So it's going to say, okay, well, let's say this is what the guess value is. So we're looking at the 4th element in the array. So we're going to go through each row in turn from 0 to 8. That's what this bit here is doing. And then we're going to assign the row of the matrix to be the row of bytes from that digit there. Okay, so that gets the player's input, and it also updates the displays to show them what the input is. So that was the first bit we did on loop. The next bit we do on loop is to call calculate response to say, okay, well, we've got a guess value now. Let's score it. Let's see how it did. So let's go and have a look at that. This is in calculate response here. So what we're going to do here, we're going to sort of set up 2 arrays of flags, because the way that you score a Mastermind thing, it's kind of quite easy to explain to someone else, but it's a little bit tricky to actually write the code for. So the way I've done it, and in fact I did link an article right at the top of the code here. There's an interesting article by Donald Knuth, who's a very famous computer professor, about the optimal ways to score the Mastermind game. But the approach I'm using here, so first of all, we're going to count the number of blacks. So we're going to start with the count of 0. We're going to loop over the entire code, and we're going to say, okay, well, if the guessed value in the ith position is equal to the secret value in the ith position, well, that's a black. So that's easy. We'll increase the number of blacks there by 1, and we'll also say that we've used that value from the secret, and we've also used that value from the guess. So that's what these 2 arrays at the top are doing here. Okay, and we'll go through that. So we'll check the entire code first of all to just get the number of blacks, and that will give us a score for here. And we've also kept track, though, of which ones we've already scored. And then we go and count the number of whites. So that's in this section here. So again, we loop over the entire code, but the first thing we do is to make sure that we haven't already scored this element when we were counting the blacks, because we don't want to count it again. So the first thing we do is we will check, well, let's make sure that we haven't already used this. And if we haven't already used this, let's loop over the code again. Well, we'll loop over the secret this time, sorry. And we'll check whether the secret hasn't been used in this position. So we're looping once over the code and against over the secret. If neither of them were used to score a black peg, but they do match, that's great. So that means that we have found a white match somewhere. And we'll now mark off the secret as having been used in this case. So this kind of happens in cases like where you have multiple occurrences of the same value. So let's say your secret code is kind of 4444, and your player guesses 4, 5, 6, 7. you want to make sure that the 4 matches one of the 4s in the secret, but then you don't keep on matching it to all the other ones. So that's the point of keeping track here as to which ones have already been used to calculate the response. That's the point of those. Okay, so we calculate the response here. And the next thing we do is, okay, well, let's call this serial update function, and that's going to send the response that we've just calculated over the serial connection. So let's have a look what that does here. So I mentioned in other code that I've written, and in plenty of other example Arduino codes, you'll find people calling serial.print and just sending a text value to the Arduino serial monitor. And you know, I do that a lot, and it's a really good way. And what we could have done is, at this point here, we could have sent serial.print and just printed the number of blacks and the number of whites, and that would have been a useful way to kind of debug the code and check the player's sort of guess. But what I'm going to do here instead is I'm going to use that Arduino JSON library, which I included the class for at the top of the file. I'm going to create a JSON document instead. So this is going to create it's still in text format, but it's going to be you know, a structured text format, and it's going to control various elements. So it's going to have an element called ID, and that's going to have a value of Mastermind. So this is because I'm going to use some monitoring software that actually has inputs from many different puzzle controllers, and I want to know which updaters come from which controller. So I'm going to assign a unique ID to start with. I'm going to pass in how many turns the players have made so far, so that's the number of guesses. And then I'm going to create an array within my JSON document that's going to have the value of the secret code that players are trying to guess. So that's secret here, and I'm just going to add 4 elements to secret, which are each of the 4 elements from the array. I'm also going to do the same thing again to show the player's last guess, and then I'm going to include the result that they got from that last guess. So this is where I'm going to add the blacks and the whites. So, you know, rather than it just being a simple 2, 3 numeric value that gets printed to the serial connection, I've got sort of quite a structure here. They're nested down relatively deep in that structure, but I've got a very obvious path to be able to retrieve that from some other software. I'm also going to say the overall state of the puzzle, and like I said, this is going to be equal to whether every element in the code was black. If it is, it's going to be solved. If it's not, the puzzle is not solved. And then I'm going to serialize that JSON object over the serial connection. So this line here, what this does is it takes this whole object that's been created up here, and it sends it over the serial connection to whatever is listening on the other side. And finally, this print line thing, this inserts a new like carriage return new line at the end of the document here. By default, serializing this is not going to include a carriage return at the end. So if you're listening for that to know when the data has been received, I'm just going to include a print line at the end. Okay, I'll explain why I'm doing that in a moment, but it seems more complicated than just calling serial.println, but actually it's much more powerful, and I will show you why in a moment. Okay, so we've called serial update, and we have returned the response from calculating the response. Let's go back to our loop function. So we've just done that bit, and now we are back to the end of the loop. So we've waited for the player's guess, we've worked out the answer, we've sent the answer over the serial connection to anything else that wants to know, so room monitoring software or something like that. And then we are, this is what's going to happen if it's not, if it is correct, sorry. So the last thing we need to do is actually display the feedback to the players on their guess to let them know, because they're not going to get that serial connection, they're going to get the LED display. So let's go to display response, and that is up here. So display response takes two parameters, the number of blacks to display and the number of whites. And like I say, you can adjust this however you want to display it in different ways. I think it looks quite nice to use that kind of the ring LED, but you could just have 4 LEDs in a row, or you could have like an LCD matrix, give the feedback of the number of blacks and whites. It's really up to you. But I'm going to display a quarter of the circle for each answer. So what we're going to do is we're going to loop over this 7 times. The reason for the loop is to allow LEDs to flash on and off. If I didn't do that, I wouldn't be able to flash them. And I'm going to count up how many blacks there were. Number of LEDs divided by 4, so that's going to give me a quarter of the circle. So for the number of blacks multiplied by the number of quarters in the circle, I'm going to light those LEDs up green. And then however far through the circle that takes me, I'm going to start from that point. And then I'm going to work out however many more whites there were. I'm going to add it to the number of blacks. I need to kind of include that as an offset. So how many whites we got multiplied by the number of quarters of the circle. And I'm going to either light them up orange or I'm going to light them up black, depending on whether the loop is even or odd. So we're looping over this from 0 to 7. Each time this is going to change between 0 and 1, because this code here means is loop an even value or not, or an odd value or not, technically I suppose. And so these are going to flash. Like I said, that's a good thing for accessibility as well. I could have just had displaying green and orange, but maybe people wouldn't be able to see what the difference between those is. So I quite like the ability to have the correct guess in the correct position being a solid value, whereas the correct guess in the wrong position is a flashing value. So that's what we've got here. And then we show that and we delay, and we just loop that a few times. And then finally, once the feedback's been given, I'm going to set all the LEDs back to black again, just to kind of reset it before they enter the next guess. Because you don't want to get out of sync between what the LED ring is displaying and what the guess is displaying. You want to make sure they're always in sync. So we'll display the guess for a short amount of time after they press the submit button, and then we will blank it out again, ready for them to input the next guess. And then we get to the end of the loop function, and that's it. So I wanted to talk a bit more about that decision to send the serial output as a JSON data object rather than just as a text string. So there's lots of Arduino Code examples that use the serial print command, and that lets you write any text string or any value, which could be like a sensor value or the state that the puzzle is in at the moment, and display it on the serial monitor connection on your PC. And that's a really good way of debugging Arduino Code to make sure it's working correctly. But the problem with that is that just a free text string doesn't have any particular structured format, so it's quite hard to interface that with any kind of control system. Now, in the window at the bottom there, you can see this is my Node-RED flow. And I've talked about Node-RED a few times in previous videos. If you're not familiar with it, it's a brilliant piece of software. It's free, it can run on a PC or a Raspberry Pi. And it lets you interface all sorts of different devices together, like Arduinos, Raspberry Pis, PCs, all sorts of other sensors, the internet services, things like that. And I use it to create an escape room control system software. So this is the flow which I'm using to receive the data that's sent by this puzzle. So you'll see it starts at the beginning here with a COM4 serial connection. So this is exactly the same as the Arduino serial monitor IDE starts with. You define the COM port that you want to listen to, and the baud rate, so 9600, the parity bits, things like that. So instead of listening to that serial print connection on the Arduino IDE, I'm listening to it in Node-RED instead. And when something gets received on that serial monitor connection, first of all what I do is I assign what's called the message payload, so kind of the flow of data that's going through this flow, I assign based on the data received. And then I kind of pass through it all. So I look at the different fields of data that have been included, and I update a value. I'm not going to go into this in huge detail here because the comments will explain more, and if you download the code you can see it. But then what I do is I have this dashboard. So this is a web-based dashboard which is on my local network, and I can connect to it on any device, so on a gamesmaster control PC or on a tablet or anything like that. And I can display values in the HTML to show the status of the puzzle. So if I show you what that actually looks like, this is the dashboard in question. You can see I've got a couple of different puzzle props all feeding into this. But at the right hand side there, you've got the Mastermind puzzle. And when players submit a guess, so if I say 240 or something like that, press the button, you can see the players are getting the feedback here, but also the gamesmaster is receiving whatever the last guess was, and also what the response that the players were sent for in terms of black pegs and white pegs and things like that. So if you've got a gamesmaster who players get stuck and they say we need a hint or something like that, the ability for them to actually be able to monitor what inputs the players are making remotely, and then they can create much more sort of useful clues because they can see where players are going wrong in the puzzle. So that's why I now kind of incorporate that in all of my Arduino code going forwards, really. It's just that interface to Node-RED, so you can display it on a dashboard like this. So I hope this video has given you an insight into both the design decisions and also the hardware and software involved in making an electronic escape room puzzle like this. The Arduino code, the wiring diagram, and also the list of links to where I bought all these components from, I will put up on my Patreon page, which is also where I've got all my previous escape room projects as well. If you would like to support me, and if you are able to support me to make more projects like this, do please head on over there, and any support you can offer would be amazing. If you can't support me or don't want to, that's fine. I will continue making these videos and putting them up on YouTube for free anyway, so you can follow along. But I hope you found this informative and useful, and let me know in the comments below if you have any questions or comments, or if you end up using a design like this in an escape room yourself. I'd love to hear about it. But until next time, thank you very much for watching.